Okay, so the question is a titration is carried out whereby 50 centimeter cube of 0.500 moles per dm cube sodium hydroxide is added to 25 cm cube of 0.500 moles per dm cube propionic acid. You have to calculate the pH of 0.500 mole per dm cube propionic acid at 25 degrees Celsius. Ka of the propionic acid is given at 25 degrees Celsius. Okay, so what is propionic acid? Propionic acid is CH3CH2COOH. This is a weak acid. It will partially dissociate into CH3CH2CO negative and H plus. We can write the acid dissociation constant of this CH3CH2CO negative concentration multiplied by H plus ion concentration divided by CH3CH2COH concentration. Okay, so Ka is given to us, and the concentration of propionic acid is given to us. So we will assume that the dissociation of propionic acid will be very small, therefore the concentration of dissociated the left propionic acid will be same as the initial concentration, that is 0.500 moles per dm cube. This we have done for the ease of calculation, and we know that the amount of propionic acid that will dissociate will give us the equal amount of propionate ion and H plus ion. So we can say that the concentration of H plus ion will be equal to the concentration of CH3CH2CO negative. Okay, so let us keep that this concentration is X. So our formula reduced to Ka equals to X square over concentration of CH3CH2COOH. Okay, so we know that Ka is given to us 1.3 into 10 to the power minus 5. That will be equals to X square divided by the concentration of propionic acid 0.500. So we solve for X. So when we solve for X will be equals to square root of 1.3 into 10 to the power minus 5 multiplied by 0.500. Okay, so this is X equals to square root of 1.3 into 10 to the power minus 5 multiplied by 0.500. So this is the concentration of H plus ion. We need to find the pH. So the pH will be negative log to the base 10 of H plus ion concentration, and H plus ion concentration is this. So this will give you the pH, the required pH. So this value comes out to be this value comes out to be 2.59. We can round it off, so this will be 2.6 pH. So this is the answer. Now the second part is calculate the pH at a point in the titration where half the acid has been neutralized. So half the acid has been neutralized means that CH3CH2COOH concentration is equal to CH3CH2CO negative concentration. So we know that the equation was CH3CH2COOH partially dissociate into CH3CH2 CH3CH2CO negative and H plus. So they say that half of this has been converted into this. So at that point we can say that the concentration of this will be equal to concentration of this. Then our Ka will be equals to CH3 CH2 CO negative concentration H plus ion divided by the concentration of CH3 CH2 COOH. And now this concentration equals to this, so we can say that this will cancel out. So our Ka will be equals to H plus ion concentration, and we know what is Ka. Ka is 1.3 into 10 to the power minus 5. So this will give us H plus ion concentration. So what we need to find? We need to find the pH at the point where half the acid has been neutralized. So pH, in order to find the pH will be equals to negative log to the base 10 of H plus ion concentration. H plus is this. So this gives you the pH equals to this will be 4.88. So we can say that this is 4.886 will be 4.89, or we can say that pH will be equals to 4.9. This is the answer. Now what they are asking in the next step, in the next question, in the next part, they are asking sketch a titration curve showing the change in pH using your answers in A and B. Okay, so what is our answer in A? pH is 2.6. So this is the pH of propionic acid. So it will start from 2.6, and at pH 4.9 half of the acid has been converted into propionate ion. Okay, so we can draw our pH curve. So on the x-axis we will have the volume of NaOH, because NaOH was titrant, and on the y-axis we will have the pH from 0 to 14, and this is our neutral line. Now the pH of this one, propionic acid, is starting pH was 2.6, so we will start from 2.6, and they say that half of the propionate ion has been converted into propionic acid has been converted into propionate ion, and that pH is 4.9. So somewhere here 4.9. So like this, and so 4.9. So our curve will look like something like this, and then this, and this is the equivalence point. Equivalence point will lie above pH 7, and half of the point where half of the propionate ion has been converted into this. So this should be 4.9. Okay, so our 4.9 will be here. This will represent 4.9 pH, this point. So at this pH, half of our propionic acid has been converted into proponate, and this is the equivalence point, and this equivalence point will be at pH greater than 7. Okay, because this is a titration of this weak acid with a strong base. and our titrant is sodium hydroxide. So sodium hydroxide is in the burette. This is sodium hydroxide, and in the conical flask is our propionic acid. Here is our propionic acid, CH3CH2COOH, and we are titrating it. So the pH at which half of the propionic acid has been converted into propionate will be given by half the equivalence point, this point, and the corresponding pH will be 4.9. Okay, so what is the last part? Last part is suggest a suitable indicator for this titration. Justify your choice by referring to a titration curve. Okay, so we need to find a suitable indicator. So what will be the suitable indicator? So we know that the equivalence point is at pH greater than 7, right? So our suitable indicator will have a pKa which will lie in this range. If we see the list of indicator that is given in the data booklet, the pH range, I think this one, greater than 7. So I think this phenolphthalein can work. Phenolphthalein can work because the pH range where it shows change the color is 8.0 to 10. I guess this can work. This also I think can work. The phenolphthalein and phenol red can work. Because the pH range is between 6.4 and 8, and this one. Okay, so the question is determine the pH of the solution resulting when 100 cm cube of 0.5 moles per dm cube chloroacetic acid is mixed with 200 cm cube of 0.10 mole per dm cube sodium hydroxide. The Ka of chloroacetic acid is given. So first we write the equation for the reaction between chloroacetic acid and sodium hydroxide. So our chloroacetic acid react with sodium hydroxide. So we know that this is a monobasic acid. So there is a reaction in 1:1 mole ratio to form a salt, CH3CONE. This is the salt and water. So 100 cm cube of chloroacetic acid is given, and this is the concentration mole per dm cube, and the volume of sodium hydroxide is given 200 cm cube, and its concentration is given 0.10 mole per dm cube. Okay, so now from this can we find the moles? From this can we find the moles? So the moles of chloroacetic acid will be volume. So cm cube we change into dm cube by dividing by 1000 and multiplied by concentration, because we know that C equals to N over V, moles over volume. So our moles will be C into V. So this comes out to be 0.05 moles. So these are the moles of chloroacetic acid. Now what are the moles of sodium hydroxide present? Volume we change into dm cube multiplied by 0.10, its concentration. So this 5, and this comes out to be 0.1 over 5, or we can say this is 1 over 50. So 1 over 50 is 150, 0.000, and 5 to the 10. So this comes out to be 0.02 moles. So the moles of chloroacetic acid present is 0.05 and the moles of sodium hydroxide present is this. So our sodium hydroxide is limiting and chloroacetic acid is in excess. So this is in excess and this is limiting. Now we know that the reaction between chloroacetic acid and sodium hydroxide is 1:1. 1 mole of this reacts with 1 mole of this to give 1 mole of the salt. So we can say that 0.02 moles of chloroacetic acid will react with 0.02 moles of sodium hydroxide to give us 0.02 moles of the salt. So the leftover chloroacetic acid moles will be 0.03. So we subtract 0.05 with 0.02. So this moles will be left after the chloroacetic acid react with sodium hydroxide. And what are the moles of the salt produced after the reaction? That will be 0.02 moles. So these are the two things that will be left after the reaction. And we know what is the total volume. Total volume of the solution will be 100 cm cube plus 200 cm cube. So that will give us 300 cm cube. So now we have the moles of this and moles of this and the total volume. Can we find the concentration of the weak acid and its salt with a strong base? Yes, we can find that. So CH2 Cl COOH, how much is left? Is 0.03 moles. So 0.03 moles divided by 300. So that will be its concentration in mole per dm cube. What is the concentration of the salt? Its salt concentration will be 0.02 divided by 300 in moles per dm cube. Now this will form a buffer solution because this is a weak acid. This is a weak acid and its salt. This is a salt with a strong base. So now we know that the pH of buffer is given by pH equals to pKa plus log to the base 10 of concentration of salt over concentration of weak acid. This is a Henderson-Hasselbalch equation. Ka is given to us. Ka of the acid is given to us 1.35 into 10 to the power minus 3. 1.35 into 10 to the power minus 3. So we just plug in the values into this equation. So we will get pH equals to pK. pK is negative log to the base 10 of Ka. Ka is 1.35 into 10 to the power minus 3. So this is our pKa plus log to the base 10 of salt is this. So this is 0.02 divided by 300 and then this will be divided by this acid. Acid is this one. So when we arrange we will get this. So this one. So this 300 cancels out. So this is minus log to the base 10 of 1.35 into 10 to the power minus 3 and this will be plus log to the base 10 of 0.02 over 0.03. So this will give us pH equals to 2.69 or we can say this pH equals to 2.7. So that is the answer. Okay, so the question is a buffer solution can be made by dissolving 0.25 gram of sodium ethanoate in 200 cm cube of 0.10 mole per dm cube ethanoic acid. Assume that the change in volume is negligible. Calculate the concentration of sodium ethanoate in mole per dm cube leave answer to two significant figures. So sodium ethanoate is given 0.25 grams. So what is sodium ethanoate? CH3CONA. So 0.25 grams is given. We need to find the concentration. Volume is 200 cm cube. So what is the molar mass of sodium ethanoate? Molar mass will be 12 plus 3 plus 12 plus 16 to the 32, 2 oxygen atoms, plus sodium mass 23, so it comes out to be 82 grams. Now in order to find the moles of sodium acetate will be mass 0.25 divided by molar mass, so this comes out to be 0.003. Let me check again. This comes out to be 0.25 divided by 82, 0.03. So this is the moles. Now in order to find the concentration, we know C equals to N over V. N is the moles, so the concentration is 0.003 divided by 200. So that gives me concentration 0.003 divided by 200, and this 200 is in cm cube, so we will change into dm cube. So we divide by 1000, so 1000 will come in here. So when we divide 200 by 1000, 1000 will go up, so it comes out to be 0.015. So this is the answer in moles per dm cube, and this is in two significant figures. This is the answer. Okay, so the next part is calculate the pH of the resulting buffer solution given that Ka of ethanoic acid is this. So sodium ethanoate and ethanoic acid will form a buffer, right? So the pH of that buffer will be given by pH equals to pKa plus log to the base 10 of salt over weak acid. So here our salt is sodium ethanoate and weak acid is ethanoic acid, and we know the concentration of salt, we just calculated it, this one, and we know the concentration of acid is given 0.10 mole per dm cube. K is given, so we can calculate pK. So the pH comes out to be, pH is pK we can calculate from Ka by the formula minus log to the base 10 of Ka. Ka is 1.74 into 10 to the power minus 5 and plus log to the base 10. Concentration of salt is 0.015 divided by 0.10. So when we solve this, pH comes out to be 3.935, so we can change to 3.94. So this is our pH. Okay, so the question is the indicator bromophenol blue HIN aqueous has a form that is yellow and an IN negative aqueous form that is blue. Write an equation to show how bromophenol blue acts as an indicator. So HIN, that is an indicator, it will partially dissociate into IN negative and H plus ion concentration. Okay, so this undissociated form is yellow in color and dissociated form is blue in color. So this is the equation. Now what is the second part? The second part states that on the addition of a strong acid, so we are adding strong acid. Strong acid means H plus ion concentration will go up because strong acid will dissociate completely to give H plus ion, so the H plus ion concentration will go up. So when H plus ion concentration go up, this equilibrium will shift towards left. So the equilibrium shift towards left, equilibrium shift towards left, and when the equilibrium shift towards left, we will get a yellow color. So this indicator will show yellow color in strong acidic conditions. Now second part, B second, is at equivalence point. So at equivalence point we will have equal concentration of HIN and IN negative. So the color will be yellow blue, both the color will be present, or we can say it will be like green at equivalence point. Okay, so the question is determine the pH of a buffer solution correct to 2 decimal places, showing the working step consisting of 10 grams of acetic acid and 10 grams of sodium acetate in 0.250 dm cube of solution. K of acetic acid is given. So acetic acid CH3COH and CH3CONH, salt with a strong base. The grams is 10 grams and this is also 10 grams. Volume is given 0.250 dm cube. This is the volume of this solution. So in order to calculate the concentration of acetic acid, we need the molar mass. We have 2 carbon atoms, so 2 into 12, that is 24, and plus 4 hydrogen and plus 2 of the oxygen, so 16 to the 32. So this comes out to be 60. Similarly, the molar mass of sodium acetate will be 2 carbon, 24 plus 3 hydrogen and 2 oxygen, 16 to the 32 and 23, comes out to be 82. So how many moles of acetic acid? Mass over molar mass. How many moles of sodium acetate? Mass over molar mass. Now what is the concentration of acetic acid? Moles over volume. And what is the concentration of sodium acetate? Moles over volume. Now in order to calculate the pH of the solution, we know that pH equals to pKa plus log concentration of salt over concentration of acid. Acid is a weak acid. So this is Henderson-Hasselbalch equation, and we can put the values in this formula. So we will get pH equals to pKa will be negative log to the base 10 of Ka. Ka is given 1.8 into 10 to the power minus 5, and plus log concentration salt. Salt is sodium acetate. We have the concentration 10 over 82 into 0.250. So this is this, and divide by so we have to take the log of all these, divide by the concentration of acid 10 over 60 multiplied by 0.250. So you can solve this. So pH comes out to be pH equals to 4.61 in 2 decimal places. So it comes out to be 4.61. So that's the answer.